Hello, this is Orlando Castilleja. Welcome to a new tutorial on the use of SolidWorks flow simulation. Today we're going to model a ball valve and we want to estimate what is the loss coefficient for this valve under different opening configurations. This simulation will be taken as your simulation number 4. The main problem is that we want to estimate the loss coefficient in a ball valve under different opening levels or configurations. We want to achieve 4 different objectives with this tutorial, and the first one is to use pre-built assemblies to model flow simulations or flow scenarios. Then we want to define multiple configurations to specify the opening angle of the valve. Later we want to specify what-if analysis for parametric sweep studies. And finally we want to retrieve data from SolidWorks to process in external softwares. We want to obtain the calibration curves of a valve for different opening angles. In this case, we want to obtain plots of the loss coefficient versus the Reynolds number. To obtain these plots, we have to define different inlet velocities. In this way, we can obtain different values for the Reynolds number, and so we can obtain different values of the loss coefficient. This simulation will have to be repeated for different angles. In this case, in this tutorial, we're going from 0 degrees to 45 degrees. For your simulation number 4, you will have to repeat this simulation ranging from 0 degrees to 50 degrees. The loss coefficient can be calculated with this expression in which we are dividing the pressure loss, the pressure drop divided by the dynamic pressure. The dynamic pressure is given by this expression, one half of the density multiplied by the velocity to the square, and the Reynolds number is given by this equation. The geometry we're going to use is an assembly in SolidWorks, and you can retrieve it from a repository online. You can follow this link to download this geometry. This geometry doesn't have the sensor or the pressure tabs, but we can generate them using SolidWorks. In this case, we're going to name this one as sensor A and sensor B, and we're going to recover or retrieve what is the pressure on this surface, both on sensor A and sensor B. We also, as I was telling you before, we will have to define different inlet velocities. In this case, I'm ranging from 0.1 to 10 meters per second. And for every single value of the velocity, we will obtain different values for the pressure A and pressure B. We're going to retrieve this data from SolidWorks, and we're going to process the information using Excel. In this case, I am calculating that the pressure drop is this value, and to calculate the loss coefficient, you're going to need the density of the fluid. So the loss coefficient is given here, and to recover or calculate the Reynolds number, you will need to know what is the value for the viscosity and the diameter of the pipe. Here we're going to use, and you can use also, this number for the diameter of the pipe. So once you have the Reynolds number and the loss coefficient, you can obtain different, you can obtain these plots. Of course, you have to repeat this table for every angle, and in this case, I am using angles from 0, 15, 30 and 45 degrees. As you can see, the loss coefficient can be, it is a function of the Reynolds number. In these cases, it is slightly dependent on the Reynolds number, and for the 45 degrees, it's a little bit more dependent on the Reynolds number. However, as you can see, it is highly dependent on the aperture degree of this valve. When you have a 45 degrees angle between the main axis of the pipe versus the handle of the bulb, well, you will have a higher loss in the energy. So, okay, we're going to the SolidWorks flow simulation, well, to the SolidWorks window, and we will continue over there. Firstly, we're going to GrabCAD to download the geometry. And we're going to look for, in the library, we're going to look for the plastic bulb, and we're going to select this one. This is the plastic bulb 25 millimeters, and maybe you will have to create an account to download this file. I have already created my profile here, and I just click download files. So here I can find it in the downloads, and I will have to uncompress this one. I'm going to move it here to a folder that I name simulation 4, and I'm going to uncompress the file. Okay, so here we will find a file that is a SolidWorks assembly document, because the assembly is composed of two different SolidWorks parts, and we will have this one, the assembly. If we open it, we just have to wait for the file to load in SolidWorks. So there you go. Here we have the assembly, and what we need to do now, well, firstly I will show you that this is completely mobile. We can move this part, and what we should do now is to draw the sensor tabs here, the pressure sensors. So what we're going to do is select this part and open part, and a new window will be displayed. Okay, it says that we have an older version for this file and we want to update this one. Okay, click accept, and here we have this single part. So I'm going to position in the top plane, and I'm going to normal 2. Okay, and I'm going to the sketch ribbon, and I'm going to select circle. So I'm going to draw a circle here and another one here. Then I'm going to use the smart dimension function to specify 4 millimeters in diameter for both circles, and I want to specify that the distance from the center of the circle to the reference point will be 35 millimeters, and also for this one 35. There you go. So I'm going to change the view, and what we should do now is to go to features and select extruded boss base. So here I think that I will have to select offset, and I will type 20 millimeters. I have to select thin feature, and I will define a thickness of 1 millimeter, and I don't want them to be on top, I want them to be in the bottom of this pipe, of this tube, So I'm going to click here and I'm going to select up to surface and select this surface. Well, maybe I will have to deactivate this part. Okay, I'm going to type okay. Okay, I'm going to cancel this operation and I will do it again so you can understand what I'm doing here. I will click extruded boss base. I will select here offset and maybe I could use a length of 30 millimeters. And here I will select up to surface and select this surface. If I change the direction here, okay, I will change the direction. So the sensors or the pipes for these sensors will be built in the bottom, and I just have to select thin feature. Okay, there you go. Okay, so remember here the configuration in the from section will be offset. You will have to specify here about 30 millimeters and you will have to change the direction of the construction. And in the direction 1 you will have to select up to surface, select the outer surface of this ball and also change the direction. Okay, remember always to include a thin feature so you can specify a thickness for the walls. Okay, there you have. But if we activate the section view, in this case for the right plane, we will notice that here we don't have access to this part of the sensor. So what we have to do here is go here to the extrude thin one and select the sketch 6 that we created before, and I'm going to extruded cut here in the features ribbon, extruded cut, and in the direction 1 I will go to up to next and click OK. So if we activate again the section view, we will notice that we already have access, the fluid already has access to this section, to this part. So that's all that we have to do before continuing with the flow simulation add-in. So I'm going to close here, I'm going to save the change, and I'm going to click yes and OK to everything that appears. And now I will have to go to flow simulation, add in. Remember that if you haven't activated this add-in, so you will have to go to SolidWorks adds in and look for the flow simulation. You can also go here to the menu and select options menu and adds in. You just have to look for the flow simulation here and activate both checkbox. Okay, so before continuing with the wizard, I'm going to click flow simulation and tools to create the leads. You have to specify that here goes a lead, another lead here, here, here. In this way, the flow simulation add-in will be able to determine what's the best computational domain for this model. So okay, well, before the wizard we have to do something else. Here we have to specify some configurations, and to do this, what do I mean with configurations? We have to define that we want to study certain angles for the opening of this valve. These angles, remember that I said that will be 0, 15, 30, and 45. So I'm going here to this part. I'm going to expand this tab here, and I'm going to select the right plane, and I'm going to select also, I'm going to click Ctrl key and select the right plane, the general right plane for this sketch. Okay, we have selected two right planes, one for the part that is the handle of this valve, and one for the general or the assembly right plane. So here, when you select both, you will have this option, angle. You can define here the angle between both right planes, and I will click or type 0. Okay, it is already fully open, and in mates, in this part, you will find this angle that you just defined, and it will be highlighted in your drawing. So you can select this one, right click on it, and I will click configure dimension. Here you have already the default that you just defined, and its value is 0 degrees. So I'm going to change the name of this configuration, and it will be 0 degrees. Okay, now we have to create the other ones, and it will be 15 degrees. Okay, we have already created all the other configurations that will be 15 degrees, 30 degrees, and 45 degrees. I'm gonna click OK. And if you go here to this tab, Configuration Manager, you can see that we already have all of these configurations: 0, 15, 30, and 45. Okay, so I'm going to the flow simulation, and we can begin with the wizard. So I will click here, wizard, the project. Okay, it can be the same name, or I'm gonna type ball. Well, I think I'm going to say that it's 0 degrees. Okay, I'm going to select here 0 degrees, wizard. Okay, 0 degrees. Next, I'm going to leave these configurations. It is okay for me, and click next. The type of analysis, it will be an internal flow, and we don't have, well, in this part we can leave it this way, and I'm going to click next. If I click here add, it will be added the default liquid that will be water, and the flow type I will select here laminar and turbulent and click next. Okay, here it's okay, and we can define these initial conditions. Finish. Okay, as you can see, the computational domain has already been defined here, and if you want, you can hide it. Okay, well, here we can define the boundary conditions. In this case, we will have the inlet in this phase in the right section, and I'm going to select this phase. Remember that you have to select other, right click on this phase, select other, and select the phase that you want. Okay, here I will define the inlet velocity, and you can use any value you like. At this time it could be 0.1, because then we are going to define a parametric sweep analysis, and in that case you will define many other values for the inlet velocity. So I will click OK, and I will define the outlet boundary condition. I will go to the other end of this valve, select this phase, and well, here is open to the atmospheric pressure, and click OK. So if you want to change the mesh configuration, you can go to the global mesh, and I will change it to a level 6 here. Okay. What else? We need to, okay, I think that it's already okay. Let's run this simulation to see that everything goes fine. Okay, the solver is already finished. Okay, what we want to determine here will be the pressure on these surfaces, the sensor A and sensor B. So we will have to go to the surface parameters section, right click on it, and insert a new definition. So I'm going to right click on this face, select other, and I will select this one. I want to know what is the pressure over here, and I'm going to click show. Okay, you will get some values, different values. For example, what is the minimum pressure, the maximum pressure, and the average. In this case, it is the same for all of the cases, and I'm going to create another definition. Well, I'm going to change the name here, right, for pressure A, and I'm going to create another definition, in this case for the sensor B. Okay, and pressure. Okay, here we have two different values for the pressures of the different sensors. We have sensor A and sensor B. So to our calculations, we're gonna recover or retrieve these values and calculate the pressure drop along this, well, past this valve. So I'm going to change here the name for pressure B, and okay, now I'm going to hide these tables, and I'm going here to this section of the window to define the what if analysis, or the parametric sweep analysis. So I'm going to position on the 0 degrees node. I'm going to right click on it and I'm going to add a new parametric study. So I'm going to define here input variables. I'm going to add simulation parameters, and I'm going to select velocity normal to surface. Why am I doing this? Remember here, I'm going to show you the presentation. So remember that we have to define different velocities to obtain different Reynolds numbers. So at different velocities, we will get different values for the loss coefficient. So these velocities will be arbitrary. You can take any values you want, as long as we can obtain different values for the Reynolds number and of course for the loss coefficient. So in this case I selected these numbers, but you can select any value you want. So I'm going to repeat this exercise, and I'm going to double click here. So I will define the other ones, 0.5, 1, 5, and 10 meters per second. Of course, you can select more numbers, define more numbers or different numbers. Okay, we have 5 different values, so the solution will be obtained for 5 different values also. So here I will select output parameters. What we have to retrieve from this simulation will be the pressures at the sensors A and B. Okay, here already shown that we will retrieve these values for pressures, and the scenario tab will show how many rounds we will have from the simulation. Okay, here we can run the simulation and wait for the software to do the calculations. Okay, the calculation is already complete, so we will have to retrieve the values for the pressure, clicking here PA and PB, and we will get these tables. These tables, we're going to copy them to an Excel worksheet. And okay, I'm going to copy this table and for pressure A and for pressure B. Okay, I'm going to define here that we have pressure A, and this is for the 0 degrees configuration. And here we have the pressure B, also for 0 degrees configuration. Okay, I'm going to, for me it's going to be useful only the average pressure, and I'm going to copy this row and I'm going to transpose it here. Here I'm going to define, we have PA in pascals, and I'm going to define on the other column PV. Also, you will have to copy only the average pressure, transpose it here, and of course you have to define here what is the velocity. In this case will be this value, this row, and transpose it. Okay, I'm going to calculate here what is the pressure drop past the valve. So it will be the difference between both columns, PA and PB. and I'm going to do it for all the cases. Okay, maybe I will have to define here what is the raw value, the density for the water, and we can define that is 997. So in this case we can calculate what is the loss coefficient. It will be, well, we will have no dimensions, and here we will do a calculation that will be the pressure drop divided by 0.5 multiplied by the density multiplied by the velocity to the square. Okay, and I'm going to repeat the calculation for all the cases. So you can also, well, here this is the value for the loss coefficient, but we want to build the plot for the loss coefficient as a function of the Reynolds number. So to calculate the Reynolds number, we also need the viscosity value in Pascal second, and this is 1 centipoise, and we also need the value for the inner diameter. Here will be meters, and I'm going to verify what is the size. Here the size or the diameter will be 3.37 to the minus 2. Okay. So in these cells I can calculate what is the Reynolds number. So the Reynolds number is the density multiplied by the velocity and then multiplied by the diameter divided by the viscosity. Okay, so here I want to change the number. Okay, there you go. So what you have to do now is to plot these values. Okay, there you have. In this case we are plotting for the case we have 0 degrees fully open valve. And so I'm going to change here is the Reynolds number, and on the other axis it will be loss coefficient. Okay, remember that the loss coefficient is defined in this way. It can be calculated in this way. So here I just want to change the color, and I'm going to change this axis to a logarithmic scale, and I'm going to define a limit from 1000 1000. Okay, that's okay. So okay, here I'm going to change the properties for the marker, and it will be a little bit larger. We have no fill, and here I'm going to change the color to purple, well, not to red. Okay. Well, for this exercise, this is okay. So I'm going to go back to the software, and I'm going to repeat this operation for every case that you have. Here I will go here to the 0 degrees node, and I'm going to click clone to copy this configuration. So here in configuration I will select, and I'm going to select now the configuration 15 degrees. So what we are creating here is another flow simulation definition, but now for the configuration with a 15 degrees opening of the bulb. So here is already activated this configuration, and what we have to do is go to the what if section. Here will be run again to under these values of inlet velocity, and what we will recover, okay, it says okay, we will recover pressure A and pressure B. Okay, I want to refresh this. Okay, and I'm going to run again the simulation. Let's wait for the calculation to be finished. Okay, the calculation is already finished, so we have to go here to this tab to copy the table, and I'm going to copy here. This is the pressure A for the case that we have an opening of 15 degrees, and we're going to copy the PV table, and also for the case of 15 degrees opening. So I'm going to copy the entire table, well, not the entire, just here, and we will change these values. Remember that we have to copy the pressure average, and I'm going to delete this part. Transpose, okay. Okay, now we have calculated a new value for the loss coefficient. And we have to add a new series of data. So here I will select Reynolds and KL. In this case it will be 15 degrees, and the other case was 0 degrees. Okay, there you have. I'm going to add the names for the data series. So by this time I'm going to leave this design configuration. Now I'm going to go back here to SolidWorks and repeat what we were doing. I'm going to change the name here to 15 degrees. So I'm going to clone this configuration. I'm going to define that we have 30 degrees now, and the configuration that we will use will be 30 degrees. Click OK. As you notice, this opening was already changed. The computational domain has also changed, and I'm going to close this one. I'm going to open what if analysis here. So I will make sure that the values are the same, but now here I have to add the results that I want to retrieve. Okay, I'm going to refresh and I'm going to click run. Okay, calculation is already finished. I'm going to copy both tables. And okay, here pressure A, and here pressure B. This will be 30 degrees. And the pressure B will be also 30 degrees. Remember that you just have to copy the average pressure. Okay, here it was 15 degrees. Okay, I'm going to run the last simulation. So I'm going to clone this. I'm going to define here name 45 degrees, and I'm going to select the configuration for 45 degrees. So I will close this window and select the what if analysis. Okay, the velocities are the same that we want to use, and I'm going to click here to define that I want to retrieve the pressure A and the pressure B. Okay, I'm going to refresh and run. Okay, now I'm going back to Excel to define here the table. So we will have to replace these values, and here we have 30 degrees. Okay, we're copying the values for the average pressure, so I'm going to transpose them and transpose them. Okay, here we have new values for the loss coefficient, so I'm going to add here the name and the Reynolds number, and finally the loss coefficient value. There you go. Okay, the software is still calculating, so I'm going to use this time to change here the colors. Okay, I'm going to use here a color green marker. Okay, I think this is already finished. I'm going to copy the values for the pressure. This is the last case that we will study, the pressure B, the pressure A for the 45 degrees configuration, and now I have to copy the pressure B for the same configuration. Okay, this is pressure B. So we're going to replace these values. I have to copy this table, and there you go. Here it will be 45 degrees, and I'm going to copy this average pressure. I'm going to copy here, and also the pressure B. Okay, remember the average pressure. So as you notice here, the value has already changed for the loss coefficient, and I will add this data series for the Reynolds number and KL 45 degrees. Okay. Okay, I just want to change the color here. For the marker, I will select purple. I don't want it to be filled, and I want it to be a little bit larger. Purple. The line will be this one, and purple. Okay, there you go. Okay, remember that we had this, initially we had this one, this plot for the loss coefficient at different degrees or different angles of the opening of the handle and the valve, and we are I'm going to copy this one to compare it. Okay, I think that we are getting almost the same values because it's the same exercise. And so in this case, what we are getting here is what is the what is the value for the loss coefficient in a valve like this one, specifically this configuration, using different angles of the opening and of the handle of the valve. Okay, this is the finish of this tutorial. Remember that you have to replicate these calculations for your simulation 4. I expect that is well explained and that you can replicate these calculations and results. If you have any question, don't hesitate to send us a message to Professor Jose Luis and to his TAs. And I expect that you are healthy and safe. See you later. What we are watching in this animation is a theoretically fully closed valve, but we could expect that this configuration will completely avoid the fluid flow, obviously, but some water is still flowing past this valve. So this is because the diameter of the pipe and the diameter of the inner ball are slightly different. So we want to propose 4 different scenarios for you to consider as your final project. The first one is that you have to modify the geometry to avoid the liquid bypass, and you also have to obtain the calibration curves as we did in this tutorial. And also you have to compare the results. The second proposal is that you have to determine the calibration curves for different beta values. In this case, beta is defined as the ratio between the diameter in the contraction respect to the diameter in the external pipe. The third proposal is that you have to determine the calibration curves for different alpha values at a given fixed value of beta. And in this case, alpha is defined as the ratio between the diameter of the ball respect to the diameter of the pipe. And finally, we want you to analyze the case where we have different ratios between the external cage radius respect to the radius of the ball. So please take a look at these proposals and let us know if you are interested. Thank you.